Good morning. Muted, William, if you're talking. It is a statement to the disorganization of myself and maybe all of us that I forgot to create the meetings until just now. I have all your notes done. I'll do the recordings today or tomorrow, get them up tomorrow, and have all the, basically have this module set up by tomorrow. I suspect we'll have two lectures in office hours as usual. The assignment for this week is actually to write a short report, and by short I mean I suspect it will be one page rather than answering a question on the assignment pages, or answering questions on the assignment pages, I should say. While we're here, are there questions about the assignment? I've got a couple good ones on Friday. I got a couple over the weekend, some clarifications. Yeah. So William, one way around that one of the faculty uses is their mic is broken, so they actually dial in twice to the meeting, once on their phone and once on their computer. So they basically have a video channel and an audio channel. So if you want to show up twice, you can do that, if it's imperative that you speak. All right, let's share. This is our last sequence in, let's see here, come on. In technology, great. This is our last sequence in the optimization. Next week, we'll move into lambda calculus. Lambda calculus is another model of computation. It's highly mathematical. The notation is a little dense and ugly, but the payoff is it is actually teaching you the syntax for functional programming languages. So not only do we get to study, again, another underlying mechanism that applies to programming languages, then we get to move into the functional programming paradigm in a way where the syntax doesn't just hit you hard without any sense of what does this all mean, because the syntax for functional programming languages are radically different than the syntax for object-oriented and imperative languages. But once you know lambda calculus, or at least familiar with it, it all makes perfect sense, or hopefully it will make perfect sense. All right, but let's talk about optimization. So again, here are the outcomes. Question, Garter, or was that a?
No, sorry, I just didn't unmute myself.
All right. So different phases of compilation, and again, different authors will use different groupings based on what they emphasize. And this is about optimization. We don't discuss code generation and assembly. However, those of you who took CS322 or 320 and 322 should probably have a really good feel for that, because effectively what you're doing with assembler is this last phase of computation. Also, if you took, let me think, if you took computer architecture, CEC 470, you should also have a fairly good feel for how this works, because basically what's happened at this point is the program has been ripped apart, studied, analyzed, optimized, and then the rest is just creating code. So the creation kind of follows a, well, we'll create assembler and then we'll move to strict machine code. So if you've had those two courses, you probably have a good feel for how that looks. If you've taken operating system CS420, you may have some idea of how that looks, because in CS420, they should be talking about machine instructions at some level. By the way, those of you that took CS420, is that true? I've never actually I've never taught the course, and I've never looked at the detailed notes for the course. So do they talk about things like the instruction fetch, execute, store cycle, or some authors do fetch, interpret, resolve memory addresses, perform the execution, and then store the result. All of those are at machine code level, and they use an assembly-like, usually an assembly-like language to get the point across. So those of you that took CS420, did that show up in the course? Or nobody took CS420? A little, if I remember. Okay, yeah, all right. Yeah, and it should be, you know, somewhat, right? Not necessarily the emphasis of the whole course. In my architecture class, they wrapped a lot around that, that basic idea. So again, you were doing like a pseudo code, a pseudo assembly code. But the whole point of this is all of you, most of you, or all of you should have some kind of an intuitive feel for, okay, all right. So if you've taken any of those courses, you already have a feel for what these last couple stages of compilation look like. You're getting into assembly, and then it's a direct path to the executable code. And I'm treating assembly as the form of machine code in which we have human mnemonics for what the operations are, as opposed to the legitimate strict 10101 binary code. All right, so let's talk about a couple things before we talk about program optimizations. One is static and dynamic binding. One is the notion of definition and use of variables, and one is the notion of intermediate representations. And we'll cover these again top level. This is kind of a survey course, so you get this stuff at top level. And then I'll give you a couple examples of optimization. Your homework will be to write, to find an optimization online somewhere, you know, find an optimization in a textbook or in a paper, and then just write, again, a brief report describing that optimization. So static binding and dynamic binding. Static binding, any binding that can occur prior to program execution. Dynamic binding is any binding that must occur during program execution. In other words, we don't know until the program's actually running what the binding is going to be. This notion of static and dynamic goes beyond binding. It goes to any property that you can think of about a program. So by static and dynamic, what we always mean in the context of programming languages is static is something that happens to the static program. In other words, the source code. You can determine it from the source code without executing the source code. The source code is just laying there, doing nothing. It's static, as opposed to dynamic, which is execution of the code. I say static relates to the source code, but it also relates to any analysis or representation that you can derive from the source code. Whereas dynamic means you have to do it during execution. It has to happen during runtime. Most of you have spent lots of time studying requirements and tests, and you know, these are by definition dynamic entities, right? How do you do a test? You have to execute the code. How do you prove your code is correct? Well, if you're going to prove it by test, then you have to execute the code. Sometimes you're allowed to prove your code is correct by analysis. At least I shouldn't say that. Sometimes you can prove that the idea of your code is correct by analysis. That would be static. But to actually prove that you implemented that algorithm correctly, you still have to do a dynamic test. So simple example, if we say x is equal to 10, we can determine the binding statically. But where we really get into the situation where dynamic binding occurs is when we don't have complete information ahead of time. So for example, if we were requiring, I guess that's a good example. Let me put it in there. If we don't know ahead of time what's going to happen, then we can't do the binding. So user input or any place where you have unknown information, that's going to be a place where you have to do the binding in the dynamic context while the program is running. And the other place, a major place where this happens is we don't know the result of the if then else. If you always knew the result of an if then else, it's always true or it's always false, you wouldn't put an if then else in there, on purpose at least. So the whole idea behind the if then else, remember this is selection. You're selecting which features of a program are going to execute. Why do you do that selection or how do you do that selection? It's based on the data that you have at the time. It's based on the program state at the time. So by definition, a meaningful if then else construct is only embedded in the code if it's going to be resolved dynamically at runtime. So in this simple case, we can't specify that y is equal to 54 or y is equal to 42 until runtime. I use foo. Foo is just the generic computer science term for a function or a method that we don't care to define. It's just a name that we use, and it's fairly widely used. And sometimes we'll use bfoo to show that it's a Boolean foo. Maybe I should do boofoo. So until bfoo is resolved and we get true or false, we cannot do the binding. That has to happen at runtime. Now, why do we care? Well, let me show the next example first, and then we can talk about why we care. It gets a little more complex than that. I mean, those were just variable assignments, right? What about function assignments? So if I have three classes, I have class A that defines foo, and then I have class B extends class A, and it overwrites foo, and then I have class C that will create an object, and the object creation is in an if then else. So either that object is created as a class A or as a class B. And then later on, we call foo. The question is, which version of foo is going to be executed? Can we answer that question statically? Well, no, because if the object creation was in an if then else, then we don't know until runtime which form of the object was created, which means we don't know at runtime which version of foo is going to be executed. Now, why would anyone care? Think in terms of stack memory management. Think in terms of program counters. Think in terms of, ideally, you want your program counter to just go next, 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 and not have to do, oh my God, I don't know what's next. Because in order to resolve that during runtime, it takes computer cycles to figure out what to do next and where to go next. Where do you go in memory next to get the next instruction fetch? Remember, if you have foo according to class A, there's actually a little hunk of memory that has the, well, hopefully little hunk of memory that has the instruction sequences for that method. And then there's going to be a separate memory set aside with the instruction sequences for the method of foo that's defined in B, the overwritten method. And ideally, when your program is compiled, all those memory references are resolved. And so the execution of the program can go smoothly. The program counter always knows what's next. When you do the fetch of the instructions, you always know where to go next. This has, let's see, I think most of you have taken computer architecture by now. This has effects on how fast your program runs, partly because it has effects on cache management. Remember, inside your, we have gigabytes of memory now, right? You have terabytes on your hard drive and gigabytes in your RAM. And now they're getting up to cache that is megabytes big, but cache still tends to be only about 1/4 of a megabyte big a lot of times. And then the chip itself, and the chip has maybe 32 memory place spaces, right? 32 registers or 64 registers, very few. So how do those 32 or 64 registers keep up with these megabytes and gigabytes and terabytes of information? They do it by just working really fast and having really clever, efficient access routines, so that when something comes into the registers, it's only there because you need it. Oh, and if you need it, it's right there in cache, ready to come in. So if you can't do this prediction ahead of time as to what's needed next in the CPU, then it can potentially slow your program down. One way to slow a program down is to have it waiting on data or waiting on instructions. So part of what the optimizers are doing is they're trying to figure out the best usage of the actual registers in the chip. They're trying to figure out the best cache policy to get the next hunks of data and the next hunks of instructions ready to be fed into the CPU as quickly as possible. And dynamic binding can screw that up. And unfortunately, you know, there's no way around it. We'll see an optimization that takes advantage of the ability to do static binding towards the end of the lecture. Okay, a couple of terms that are widely used. Def and use. Def is where the binding to a variable is defined, and use is where the binding is used. So by def, remember we talked earlier in the last week about the program store, this notion of variable value bindings. That's a direct correlation to memory, where you say there's a memory location associated with a variable name, and we put a value in that memory location. Now that variable name is now bound to that value. How is it bound in the real world computer? Every time you see that variable name, the computer is programmed to go to that specific memory address and retrieve the value. How is it bound in a more theoretical sense? We have the store, which is lists of variable value bindings. So wherever we create a variable value binding, we can call that a def, short for definition. And whenever we use them, that's called a use, which is not short for use, it's use. So we have variable value bindings used and defined. And then you can start to look at threads of definitions and uses. Liveness are all the points in a program where a specific definition is alive. So for example, in this example of code I have that only has 5 program statements, I have a definition for X in statement 1. So that would be a def node or a def statement. And so once we've defined that value for X, then in statements 2 and 3, we use X. And then in 4, we have another definition. So that kills the old definition and it creates a new definition. Remember, in terms of semantics, we said it removes the old variable value binding and replaces it with a new variable value binding. So it kills the old definition. So in other words, the def that was performed in statement 1 is considered to be live in statements 2 and 3, and then it's dead. And then a new one is created in statement 4, and it's considered live in statement 5. Incidentally, statement 2 is a def for variable y, statement 3 is a def for variable z, statement 5 is a def for variable p. I just happen not to use them. Right? Now, one of the things that works with optimizations is you can manipulate the sequences in which things are performed as long as you don't modify these liveness of the def use. That can be really restrictive. You know, if you use the same variable, like you've got kind of a generic variable that you use just as a temporary record keeper in different points in your code, then that can be somewhat restrictive. But there are ways around this. Let me see on the next slide, and then I might come back to this one. Yeah, so here's some examples. Def and use sequences changes are limiting what the compiler can do. So for example, program A, that's the original program that we had. Program B, all I did is I swapped out statements 2 and 3. Are we allowed to do that? Do you think we would be allowed to do that? Between program A and program B, are those two programs equivalent? Yes. And why is Casey right? What is the basis that she is using for program equivalence here? Should I keep the chat up? Isn't that the worst question? Why are you right? Let me ask it this way. Is there any difference that we can see in terms of observable input-output behavior between program A and B? The coordinates change, but the results are the same, right? So in terms of observable input-output behavior, or if we wanted to, we could say observable modifications to the store, transformations to the store, they're exactly the same. So it's just a simple switching of two program statements. Now, I'm not saying that's going to be a great optimization. I'm saying that concept is that you can start to move things around. In that particular case, why might a compiler choose to move things around? Well, maybe variable Z is already in the register and variable Y is not. And once you get something into the register, you want to do everything you're going to do with it as much as possible before you get it out of the register. Because if you get it out of the register and then you need it back in later, you're wasting cycles, right? Just shipping things back and forth from memory to register. So one of the goals at the chip level is once you get something into a register, use it as much as possible. Oh, and by the way, if you can reorder your program so you don't even bring it into the register until you're going to use it, that's helpful too. So there is no difference between program A and B in terms of observable input-output behavior or in terms of observable store transformation. But look at program C. Now there's a problem because statement 4 is using what I'm going to call the wrong value for X. I've moved that P ahead of the second def statement for X. And program D is the same thing. Now I've moved statement 3 after the second definition for X, and now it's using the wrong value for X. And you can ask yourself, well, okay, these are really obvious, Garfield. This would never happen. Don't kid yourself. These are simple examples, but remember the job of the compiler. The job of the compiler is to take your program apart and put it back together in a efficient way. And as we'll see later, one of the things the compiler does is it takes what you think is one programming statement that you in your mind says happens atomically, and it'll rip it apart into a bunch of tiny little computations. And those computations may not all happen at the same time because remember, you're sharing your processor with a bunch of other processes. So it gets halfway through that computation, somebody else gets the processor for a while, somebody else changes the registers or changes the memory, and then your process comes back and what used to be variable X is now magically changed. And again, remember, this was a big enough problem that it largely inspired the entire object-oriented paradigm. This is not a trivial thing. Oh, and by the way, now we live in a parallel environment where it's even worse because a remote CPU might come and overwrite your memory accidentally if people aren't careful about how they do these things. So these are really simple examples. and you think, okay, couldn't possibly happen. But it's not a bad thing to be aware, particularly in our multi-process world and hyper-threaded world. Be aware that you may have opportunities in your software in a post-compiled version for something to go wrong, where you may have race conditions. You've all studied race. Again, in operating systems, you studied race conditions. I'm not sure if you did in computer architecture. And you may not actually be able to definitively say what the value is for a particular variable or in a particular memory location. And it's the job of the compiler to be as aggressive as possible to get efficiency without creating these opportunities. But it's not a bad idea for you to be aware that these opportunities exist, particularly when you guys get into working in networked and parallel and distributed systems. These things can come up. And they don't just become programming robustness issues, they can become security issues, because anytime you have a program that goes into an undefined state, that's the situation that hackers try to take advantage of. Okay. So this notion of def use is going to be used, and this is why we're talking about it, that the compilers do have to worry about the liveness, and there's actually some more criteria that we'll get into in a little bit. All right, now, in order to get this optimization to occur, some kind of program analysis has to happen, and along the way, that means that the representation of the program will change. Your program actually changes its representation multiple times as you go through the compilation process. We've already seen that your program can be represented as a parse tree for syntactical checks. You can get into, well, let me show you something else. You can get into situations where you have some fairly benign changes. For example, one way to not worry about liveness, even though you, the programmer, just kept reusing X because you like to use X, and you kept reusing it. Was it just a generic useful variable for you that you didn't really care about, so you reused it in parts of your code? It's very likely the compiler is going to do this. And look what that does. Now it separates those two def statements in the groupings of use statements that are applied to them. And now the compiler has a lot more freedom. Remember, the names you give your variables are for your value. They are used in the source code to clarify the source code if you're naming things well. And then the compiler will absolutely ignore those lovely names that you spent a long time thinking up and replace it with other tokens. And if it can replace it in a way of other tokens that is going to be helpful in terms of future optimizations, it will. So that is not an unreasonable thing for a compiler to do. It's called single assignment. Each variable in the program actually only gets assigned a value one time, only one def statement. Wasteful in terms of memory? Maybe. In the short run, it may be, but in the long run, after the compiler is done doing all the optimizations, a lot of those might go away anyway. Okay, so intermediate representations. Your program, that would quite frankly be an intermediate representation right there. The idea behind an intermediate representation is that your program does go through all these different transformations as it goes through the process, and some of them are quite radical. So we have the parse code. One form that we'll discuss here are program dependence graphs because they're widely used both in compilation and in program analysis. And forms like 3 address code, which again are in the notes here. But there's different forms. You guys already know this. You know that you can have already represented, at least some of you have represented your code in EGR 115 and CS223. You probably represented your code as a flow chart. Before you did it before you wrote your code, right? You planned out your code using a flow chart and then you wrote your code. At least if you were doing the process correctly, you were. But now we can take that process backwards. Once you write your code, I can reframe it as a flow chart, and I can frame it as a data flow chart where I look at which def use pairings are important, or I can frame it as a control flow chart where I'm looking at how the selection of program statements is made and what are the critical points in terms of choosing true, false branches or paths through the program. So you already intuitively know this. The goal of an intermediate representation, by the way, is again, it's called intermediate because it's not the source code, right? The user sees the source code. And it's not the machine code. The computer uses the machine code. Those are the endpoints, right? Those are the beginning and the end point of the compilation process. The intermediate representations are used at the intermediate points in the computation process. Nobody sees them. The machine never sees them to execute. The user never sees them to code. So they're intermediate. They're kind of hidden. There are a whole world of programming representations / languages that nobody knows about because only compiler people will talk about them. The goal of an intermediate representation is not to be language specific. It is to, if you look at a program that is given to you in intermediate form, you should not be able to identify the programming language that it came from. You may not even be able to identify the paradigm that it came from. So there are universal representations of programming processes. And they're used to perform the analysis, sometimes syntactical and parse trees, and sometimes semantic, and sometimes optimizations. And the program dependence graph form is more about the optimization. The way the semantic analysis works is we've seen briefly last time, if you had a bunch of, let's say an axiomatic semantics where you have a set of preconditions and postconditions for a specific programming statement, you might actually associate that statement with the set of pre and the set of post, and in a graphical form, and we're going to move into graphical form in a little bit. That actually ends up being what they call decorating the graph. In other words, there's a node on the graph that has some content, but then attached to that is like a footnote. And then the footnote says, hey, go here, there's a bunch of metadata here. I think what we'll do, let's talk about this 3 address code, and then I'm going to save program dependence graphs for its own lecture because it's a sophisticated enough topic that I don't want to try to rush it in the last few minutes here. And so this will be a good stopping point. But this is what I'm talking about earlier, your code that you spent, all that lovely code you wrote, right? It gets ripped apart. And one form of intermediate representation, this is actually typically towards the latter end of the compilation process, is this notion called 3 address code. And it's called 3 address code because you have at most 3 operands. There we go. You have 3 operands. You have an operand, an assignment operator, and then you have 2 operands on the other side with a binary operator, at most. Now, you may not even have that. Like here in T8 is equal to 2 times A. So there's a it's a binary operator, but you only have one variable on the right hand side. Here's a unary operator, square root of T4. So these T's, they're using T's as a mnemonic for temporary, right? And what you do, you know, think about how you actually do an equation. If you were to do this equation by hand, good old-fashioned math, pen and paper, algebra and calculus, how would you do it? Think about what you do. You always do one thing at a time. One binary or unary operation at a time. So nobody, that's not necessarily true, nobody that I know or have ever met would take this equation and literally do it all at once. Even if they did the whole thing in their head and wrote down the solution, they're still in their head doing one thing at a time and keeping track of their intermediary result. And so it's the same thing here. What do we have? This is the, it's quadratic formula. I'm trying to see if they got their parentheses right. So here's the quadratic formula. And if you break this down, you say, okay, 2 times a, that's one thing I can do all by myself. And you may or may not choose to do that first. Or you can do the b squared first, or the 4 times a, and then that temporary result, 4 times a times c. But you would do that as 2 operations, right? Nobody multiplies 4 times a times c. They multiply 4 times a and take that result and multiply it by c. And maybe you change your sequence based on those specific numbers sometimes, because, you know, some numbers are easier to multiply in groups than others. But you can see on the right how they break this down into its component parts. So they start out with the b squared, right, T1, and then they take the 4 times a, that's T2, and then they take T2 times c, well, that's 4 times a times c, and that's T3. Then they take the b squared minus 4 times a times c, that's the T1 minus T3. Then they take the square root of that. And then, interestingly enough, they don't do T6 is equal to T5 minus b. They do T5 is 0 minus b. Why? Because that minus is an operation. And if you were to do, you would almost think of that as 2 operations at the same time if you did it wrong, right? Minus b plus T5. Minus b plus T5 is actually 2 operations. So they do the minus b operation first, and then they do the T plus 5 operation top. Now they've got the numerator. T8 is 2 times a. Now they've got the denominator. And then they do T7 divided by T8. Now they've got the actual result. That's how your code gets broken up. And you can see in this sequence of 9, 10 statements, if you lose the processor to another process at any point in time, you have an opportunity to come back and have values inadvertently change. Now, it's not likely to happen. A good compiler will take care of it. A good hyper-threading operating system will take care of it for you and protect you. Not likely to happen, but it's possible to happen. If you're in if you're in a multi-threaded, hyper-threaded, or a parallel environment, you know, these kinds of things may happen. Once you get down to these little statements, your whole code is represented this way. It's basically ready to be converted to assembler and machine code really quickly. I mean, those of you that are familiar with assembly, this looks kind of similar, right? But instead of using these temporary variable names, you're going to use registers, register IDs, accumulators, that kind of stuff. So this is pretty ready to be this is pretty close to being turned into assembler code. And along the way, you can do what are called keyhole optimizations. And again, this usually goes to register use. If I'm going to take, let's take T2, T4, T5. Let's take T8. T8 is 2 times a. I could have done that first, right? The first statement could have said T8 equals 2 times a. But then I didn't use it until T9 down here in the 9th statement. Well, meanwhile, T8's hanging in there taking up a register. And maybe I run out of registers and I have to ship T8 back into memory. And then later on, I have to bring it back just to do T9. So that's inefficient use of registers. So this notion of at this level, doing these little tiny optimizations. They're called keyhole optimizations because you're only looking at little teeny tiny pieces of code instead of the larger code as you are in some of the other optimization forms. And so when you're doing these little tiny optimizations, it's called keyhole because you're just looking through the keyhole, right? You're looking at just that little part of code. You can only do so much with the optimization there. And again, as I keep saying, it's often related to register allocation. And by the way, if you remember way back in CS332, hopefully we talked about an NP complete problem called graph coloring. It turns out that the way that you actually try to solve the best way to use your registers is through a graph coloring problem. You map register allocation to graph coloring in a node. And if you can't remember graph coloring, you know, I'm happy to talk about it all day. All right, I'm going to skip ahead to show two concrete optimizations, and then on Wednesday we'll talk about the program dependence graph, which is another intermediate form. You are not on the hook to remember or produce things regarded to the program dependence graph, but I think it's worth looking at. And again, I have a soft spot for them in my heart because, as you'll see, I stole all my material from my PhD dissertation, but they are widely used. They are real live analytical tools. It is also helpful to be able to represent your program in graphical terms at times because graphs are such a flexible and widely used form for all kinds of data representation, including programs, and it can help you be a better programmer if you are familiar with not just the program dependence graph, but graphical forms in general of representing things. All right, so I'm skipping ahead. Here's two examples of optimization. They're both fairly straightforward. One is called constant propagation. So you wrote this in your code, and I'm not saying these lines came, you know, these lines didn't necessarily come sequentially like this. Maybe they're separated by other lines of code. Maybe they're separated by hundreds of lines of code. But all of the definitions are still live. So once we get down to, you know, we're still good here, okay. Right here, I can say x equals 10, y equals 5, z equals 5 times 10. Oh, that's z equals 50. That's pretty easy, right? What I mean here is, here's my text. There we go. So the first thing is, if x equals 10, you know, what are you saying? Set up a memory location and put the value 10 in there. And then later on, you use that value. And what are you saying? Go to that memory location called x and grab that value that's in there. Well, heck, if the compiler can already figure out what's in there, why would you waste the computer cycles? Why would you ask for another memory fetch if you don't need it? By the way, memory fetches can be really expensive because if you can't find the thing you're looking for and you're waiting on it, you can burn up hundreds of thousands of computer cycles just waiting for the memory fetch. Unless you've got a really good chip and operating system. So this whole thing, these three lines of code, which involve what? One memory store, one memory store, one memory fetch, one memory fetch, one memory store. That's 5 total operations, gets reduced to one operation of just here's a memory store. And this propagation can go on so that if we know, again, if let's say Z is used somewhere else, then you can replace that Z value with 50 wherever it's used. Basically, if you ever write a program, you know how when you first wrote your very first programs way back when you were a computer science kid and you wrote like a temperature conversion program, but there was no user input, you just put in hard-coded values for the temperatures, that kind of thing. That's a typical first program with no user input. That's the key. The bottom line is the compiler could have actually performed the whole computation without doing any execution of the code. The whole code just reduces to whatever the output is. So that's one thing. Now, the place, we'll talk about this in just a second. Another version of this is you have an if then else in there, but remember in axiomatic semantics, we were asking questions like, is X greater than 0 at this point, right? And if you can definitively prove, say that X is always greater than 0 at that point, then you know that the true branch is going to be executed all the time. In this case, you could do static binding, and you could say, well, we know that the true branch is going to be executed, so I'm going to get rid of the if then else, and I'm just going to put the true branch in there. Now, you may not be able to do that. Most of the time, you can't do that, but sometimes you can. And you're reducing the cost of, again, doing the Boolean check, maybe calling a method, which could be a large computational cost, and the indecision of the program counter. All of those things can be satisfied. Now, these kinds of line-by-line optimizations are not where you tend to make a lot of money in terms of true efficiency. Where does your program spend most of its time? In its loops. So where do you want to attack efficiency? In the loops. So here's a simple loop optimization. I'm going to replace this simple loop for I equals 0, I less than n, I plus plus, my array I equals foo, right? So I'm going to do something to the ith element of the array every time through. But what happens with a loop? Oh, wait, every time you go back, you have to do a check. Oh, and if you ever get false, then your program counter is wrong and you have to, reset your memory stack and blah, blah, blah. So what's one way to do that? Well, one way to undo that is to do what's called loop unrolling. And in this case, I unrolled it 5 times. So instead of I equals I plus plus, I go to I equals I plus 5. And now I can do my array, and I just keep modifying the index values so that I catch all 5 of for every single loop through the second form of the loop, I catch all 5 of the array items that I caught going through 5 passes of the loop the first time. Why is this of value? Well, again, it reduces the checks that you have to do in terms of, do I keep continuing the loop? And the loop stopping, so the loop stopping condition is check left, but also this uncertainty of, gosh, I don't know what to do next. Well, at least for the next 4 statements, I know what to do next. If you can verify n ahead of time, if you can do that during the compilation process, you could replace that whole loop with straight line code. Now, is that efficient in terms of memory space? Not so much. Is that efficient in terms of execution time? Yeah. So there are some, sometimes there's trade-offs here. But these are the kinds of cute tricks that people have looked at over the decades to get compilers to become efficient. Now, one advantage, by the way, of the second form, remember, we live in a highly parallelized world. Even your, quote, one computer has probably 4 chips inside of it. Each one of those statements could be sent out individually to one of the 4 chips. And now we can do those 5 statements in parallel. There's another speed up. So you can play all kinds of games with optimizations. And I mean all kinds of games, right? There's a lot of people getting their master's thesis and PhD dissertations on compilers. Now, having said that, again, I'll preface this again. I highly doubt any of you will ever actually design your own compiler. It may happen, but you may have to do clever tricks with data processing. You can use these same tricks. You may have to parallelize programs. You can use these same tricks. So that's the value of these. So your assignment for this week is going to be find an optimization and write a short paper on it. I'm thinking probably 1 page, 2 pages, that provides the description of these things. And what we'll do on Wednesday is talk about the program dependence graph. And then on Friday, we'll have office hours. and I will catch the Canvas stuff up to speed on by Tuesday night, tomorrow night. Okay. Have a good one.
Bye. Thank you, Professor.
Yep.
Thank you.
Bye.